Alright everybody, how are you? So today we're going to finish up our periodic table videos, and this time I'm going to talk to you about electronegativity trends. So if you look back in the notes, you'll see that electronegativity is defined as the attraction an atom has for electrons in a bond. So when two atoms are bonded together, both of their nuclei are pulling on the electrons in the bond. And depending on that size of the nucleus, if you think back to terms like effective nuclear charge and shielding, those all determine the electronegativity, how well an atom is attracting electrons in a chemical bond. And what we see is the same trends we saw with ionization energy, and for the same exact reasons. So, going down a group, we have electronegativity decreasing, and going across a period, we have electronegativity increasing. Now, why do we have electronegativity decreasing? Well, the same reasons that we had it for ionization energy. You have an increase in shielding, where you also have the Zeph staying constant. So because of this increase in shielding and this basically constant Zeph, you get less attraction between bonded electrons and the nucleus. So, that's sort of what's going on, where we have this increase in shielding, and we have this same Zeph when we go down a group. Now, when we go across a period, what we see happening is that the electronegativity increases, and the reason why has to do with the relatively constant shielding and the increase in Zeph. So what this does is this leads to a higher attraction between bonded atoms and electrons, bonded electrons and a nucleus. So this is our trends in electronegativity, and I don't talk that much about it. I just want to sort of introduce the idea to you. You don't see those same blips and those same, exceptions when you think about electronegativity. And really the main reason why you don't see that is just because electronegativity, it's like a fake scale. It's based on real things, but it's a scale that doesn't have units. It's a scale that Linus Pauling invented in order to sort of iron out all of those weird sort of inconsistencies you see with other things. And it gives you a general idea about how reactive an element is, if it's going to lose or gain electrons when it reacts. And when we do bonding, you're going to see we're going to keep going back to, this element lost electrons, this element gained electrons, these two shared electrons. And it has to do mainly with this idea, and it correlates very closely to electronegativity. So now, if I go down to this next slide here, this just generally lays out all the properties of the different types of elements. So for metals, you should know that they tend to have good conductivity. And they mainly have good conductivity because they have mobile electrons. If you look at the ionization energy and the electronegativity of different metals, you'll see that they're generally low. And because of that, their electrons are mobile throughout the entire substance. When we do metallic bonding in the next chapter, we'll talk more about this. They have luster. They generally have high melting points, with the exception of a few like mercury or maybe cesium, but generally their melting points are pretty high. And they tend to lose electrons easily. They tend to have low ionization energies. They tend to have low electronegativities, and they tend to have high atomic radii. Now, if I go to a nonmetal, we see a lot of the opposite types of things going on. So, for example, we see things like poor conductors. We see that they are brittle, that they're lackluster, that they have low melting points, that they tend to gain electrons. And this is mainly because of their high ionization energy, their high electronegativity, and their small radii. Something else I want to add about metals when we think about properties, and we mentioned this in the first chapter, and just a little bit of review, the metals tend to be malleable and tend to be ductile. Now, why did I leave metalloids out? Well, I left metalloids out because they're sort of a blend of the two. You'll see things that are what are known as semiconductors. So they conduct electricity, but not as well as a metal. You'll see things like some of them are lustrous. If you look at some of these metalloids, you go to periodic videos and you watch some of those videos, you'll see like, wow, this has luster to it. Whereas some of them, tend to be, non-malleable. So they have a mix of the two. So these tend to be mix of metal and non-metal properties. When we talk about bonding, though, when we look at metalloids, they tend to behave more like nonmetals. So they tend to be closer to nonmetals in terms of, high ionization energy, electronegativity, and small radii. Okay, some transition metal details. Really, like we went over with the transition metals, groups 3 through 11. They are part of what's known as the D block. And because of this, and I have this nice picture of Starry Night here, and the reason why I have this is because a lot of these compounds that contain these transition metals, they actually have colors to them. So copper is a common one. Copper has this nice, when it's +2 ion, it has a nice blue color to it. Cobalt, in its +2, I believe, is a nice blue color. But you could actually have cobalt as +6 and have it be pink. Something else that's cool about the transition metals, another color, manganese +7. If you're going to take the SAT, they love asking about manganese +7. It has this awesome dark purple color to it. And this has to do with the electrons moving between the S and the D sublevels. They're so close to each other that when we talk about excited and ground state, we actually can look at this and be like, oh yeah, we can have where the electrons can become excited and move between the S and the D sublevels so easily. And that gives off colors even without putting energy into them outside of the normal energy they can absorb. Okay, specific details about specific elements. So you should know, for example, that fluorine, it is the most reactive metal. And you should know that fluorine is the most reactive non-metal, and francium, I was thinking ahead here, is the most reactive metal. You should also know that hydrogen, although it's on the metal side, it is a non-metal. So it is a non-metal, but it's living on the side of the periodic table with the metals, and we talked about this in class, but it's important that you understand that. Something else that's sort of cool is that copper, it is the most conductive metal. And so we see this when we look at people's homes. Their wiring is done using copper because it conducts electricity better than any other metal. They used to use aluminum, we could talk about that in class, but aluminum ended up getting really hot and it would catch fire, and so that's really a big safety hazard. It's not what is coded for now. With ionic versus atomic radius. So with ionic versus atomic radius, if you are a negative ion, then you are larger than your atom. And if you are a positive ion, then you are smaller than your atom. If you're wondering where some of these names come from for these elements, here's a list of some of them that are kind of cool. So I will look through these. Some ones that are really sort of neat, like mercury. This actually stands for liquid metal hydrogyrum. If you've ever been to Argentina, the land of silver, Argentum. Sodium originally was natrium. If you're wondering why do they torture me and make sodium Na, and that's why it actually comes from the name natrium. So there's a bunch of them here that are kind of cool. If you want to go really crazy, if any of you actually understand or can read Chinese characters, this sort of gives you a list of the elements in Chinese characters. One last thing, and what I want to close with, and this is going to sort of tie into our next unit, is what happens to elements when we look at different ones. Why are they so different? So when we look at lithium, we know it has 1 valence electron. Carbon has 4 valence electrons, and fluorine has 7 valence electrons. When we look at the number of protons, lithium has 3 protons. Carbon has 6 protons, and fluorine has 9 protons. And when we look at energy levels, we have N equals 2, N equals 2, N equals 2. And so what I want to leave you with is when you look at this and we look at how they react, we see that lithium will tend to be a plus ion when it bonds and when it forms compounds. And we see carbon could go either way, plus or minus, and fluorine will always be minus. And so what I want you to think about is, why is that the case? When we talk about this in class, which we'll do when we introduce the idea of chemical bonding after next week, we'll start that on Monday, I want you to really look at these and say, why does fluorine gain? Think if you can explain it in terms of what we did in this chapter, the terms of atomic structure, and how they relate to things like ionization energy, electronegativity, and atomic radius. All right, thanks for watching, and hope this was helpful.